discuss this Leetcode hard problem. Uh, it has been recently asked in weekly contest. Uh, so it is minimum cost walk-in weighted graph. Okay. So what we have given in this problem, we have given an undirected weighted graph with n vertices, which are from 0 to n minus 1. Okay. And we have given an edges vector, which is describing the details of edges. So it is saying if there is an edge from ui to vi which is having weight wi. This description is given in this edges vector. So after this, it is telling us what a walk on a graph is. So according to this problem, a walk on a graph is a sequence of vertices and edges. The walk starts and ends with a vertex, and each edge connects the vertex that comes before it, and this. Okay. So the important thing is to note the walk may visit the same edge or vertex more than once. This is an important information given in this problem. So according to this, basically the walk is nothing but you can visit any node and any edge more than once. There is no problem in this. Walk is just a sequence of a, like you can say it's a path where you can visit any node or edge more than once. This is simply what walk is. So the question is asking us the cost of walk starting from u to v is given. Oh, so basically it is defining cost of going from u to v. It is not the summation of costs. It is basically the bitwise and of all the weights. It is saying, let's say you are going from u to v. There are some nodes in between. Let's say it is something like this: w0, w1, w2. It is saying कि the cost of going from u to v, that is cost from u to v, is it is defined as bitwise and of these things, these weights. I think now it is clear. It is not the sum of weights, it is bitwise and of all these weights. So what we have to do in this problem is, it is saying we are given a query vector where we have starting point and ending point, and we have to find minimum cost from start to this target node if there is a walk existing. Otherwise I have to answer minus 1. Okay, so let's first see what the constraints are. So the constraints for this problem is n is up till 10 to the power 5, and the m, which is the number of edges, it is also up till 10 to the power 5, and edge weights are positive, right? Non-negative, right? So it's an shortest path type problem where the cost of path is defined as the bitwise and of all the weights of edges. Okay, so if we think it's a shortest path problem, and shortest path problem is generally solved using Dijkstra algorithm. Okay, so let's say Dijkstra or flood Warshall, because it is not single source Dijkstra. It's not a single source shortest path problem, because for each query we have different source and target. Okay, so yeah, so yes, so I was saying uh, कि this problem is based on shortest path. In general, we solve shortest path problem using Dijkstra algorithm or flood version. I am saying flood version because there are multiple source and targets in query vector. So let's think for in Dijkstra algorithm, for single Dijkstra the time complexity is almost n log n, whereas for flood version the time complexity is n cube. So let's say in worst case scenario, for let's calculate the time complexity for both these algorithms for all the queries. Okay, so for q queries, it will be, if I am using Dijkstra algorithm, it will be q times n log n, big O of q times n log n. And in case of Floyd version, it will be q times n cube. And as we can directly see, q is also up till 10 to the power 5, n and m are also 10 to the power 5. So both of these solution will give me TLE, right? So I can't do this. I have to think something else. So okay. So let's think. First of all, here the cost for path is bitwise and. So let's analyze this first. So what kind of a function is, like, if I am taking bitwise and of many elements, what is its behavior? As we can see, bitwise and is like, if in a function I am taking bitwise and of multiple elements, I can directly see that the output of this function is decreasing, because and bitwise and is decreasing function, I can say. Uh, so like if I want to have minimum distance, or like minimum cost of path uh, in walk from source to target, that means if I am let's take this example where this graph is given to me. Okay, so here in this query, the source in first query, the source is 0 and the target is 3. Okay, let's first see if I am able to go from 0 to 3. I can go from 0 to 3 in this way. Wait, let me take this highlighter. Yeah, I can go from 0 to 1, then I can go to 1 to 3. In this path, or in this walk, the cost will be 7 and 7, which will be 7. Okay, if I take all the edges, let's say I go there 0 to 1, then 1 to 2, then again 2 to 1, and 1 to 3. As it is given, the it is walk, not the like simple path. In walk, I can repeat the edge and nodes. So I can go from 0 to 1, then 1 to 2, then 2 to 1, and then again from 1 to 3. In this type of a walk, the cost will be 7 and 1, and again 1, again 7. It will be uh, what it will be? It will be 1, because 7 is 1 1 1. If I am taking its bitwise representation, 1 is 0 0 1. If I am taking and for this is 1 0 0. This is just 1. So as we can directly see, uh, bitwise and operator is a decreasing kind of a function. For minimum distance from for minimum cost from source to target, I need to consider all the edge weights. So I have to take all bitwise and of all the edge weights uh, of the component in which there is source and target. So let's consider two types of case here. Case 1, when source and target are in same component. In this scenario, I have to take bitwise and of weights of all edges, right? Of that component, particular component. Case 2 is when S and T are not a part of same component, not in same component. You can easily think, if these are not a part of same component, I can't go from source to target node. That means uh, this type of walk, there is not a single walk possible for these pair of source and target. So in this kind of scenario, I have to print -1. Okay, so to handle these type of things, obviously I can't do Dijkstra, I can't do Floyd Marshall in this type of problem. So what I have to do is I have to do some kind of a pre-computing, right? As you can easily as you can see here, in case 2 the answer will be -1, and in case 1 the answer is bitwise and of all the edge weights of component. It is independent of the value of source and target. By this thing we can directly see that there is a pre-computation involved here. So let us pre-compute the bitwise and for all the components first, then go to the query parts. I guess this will work. So for pre-computation part, the first thing that comes to my mind is use of disjoint set. So let's illustrate a example let's take this, yeah, this kind of test case. So in this test case, the edges are like 0 to 7, 0 to 7, then 0 1 15, 0 1 15. After 0 1 15, we are having 1 2 6 and 1 2 1. 1 2 6 and 1 2 1. Okay. So let's dry run this joint set part on this test case. So these are UI values, these are VI values, and these are W values. Okay. So first of all, initially we can initialize the disjoint set as usual. This the new thing to this disjoint set is the AND values for the nodes. We will see this in coding part. So let's just dry run this part. Okay, so there is node 0, there is node 2, and there is a edge of weight 7. Okay, so now initially these were like this, 0 2. When I consider this edge, the disjoint set will be like this, let's say like this, 0, and the parent of 2 is again 0, right? Now for this edge, 0 to 1, after this edge, the disjoint set will be something like this, right? After this, 1 2, the disjoint set will be something like this, again like this. These 1 and 2 are also a part of same component, and this, let's take this as, because this test case is containing two different components, let's take this test case instead. So here we have these 0 1 7, 1 3 7, 0 1 7, 1 3 7, and again 1 to 1, right? So these are the edges given to us. So initially the nodes are like this. The parent of 0 is 0, parent of 1 is 1, parent of 2 is 2, parent of 3 is 2, parent of parent of 3 is 3. How many nodes are there in this test case? So there are 5 nodes, 0 to 4. Okay, yeah. So parent of 4 is 4. Okay. So when I consider this edge, there is an edge from 0 to 1. The disjoint set will be something like this. Parent of 0 will be 0, but the parent of 1 will be 0, right? So after this edge, 1 to 3, the disjoint set will be something like this. I am using path compression here. So yeah, the parent of 3 will be 0. And again, after considering this edge 1 and 2, the disjoint set will be something like this. The parent of 0 is 0, the parent of 1 is 1, the parent of 3 is 0, and again the parent of 2 is also 0. And the last node 4 is separate, and its parent is 4 itself. Okay. So after considering all these edges, we can directly say there are two components here in this graph. So if the source element is in same component, then I have to what? I have to calculate the bitwise add value of all the edge weights in the particular component, and I have to return that. If source and target are belonging to different components, I have to directly push back -1 to the answer vector. So let's now directly go to the coding part of this question. Yeah, this is the code. I have already coded this question. So what I have done in this problem is, this is just macros and like defining. Okay, so as we usually do in disjoint set type of questions, this is just get parent function. If a is equal to the parent of a, we just directly return it. That means there is single component in that, there is single element in that component. Otherwise, mark the parent of a as the leader of that component. This is path compression, which uh, reduces the time complexity of that function. This is the union, or we can say merge function, in which in a usual merge function we don't have this weight, but in this merge function I have to consider and value of the nodes also. So I have taken this w here also. So first of all, I have changed a as leader of the a component, b as leader of this component of b. If the size I have done this thing just to make sure that the a is the leader of bigger group. So after that, what I have done is I have updated the and value of the a as like I have taken and of this value with and of b also. Then with this edge node also. Then this is just simple disjoint set part. Size of a is updated is incremented by size of b, and parent of b is marked as a. Okay. So first of all, I have to initialize all these things in this particular vector, in this particular function. So yeah, what is n? N is the number of vertices. 0 to n minus 1 are these vertices, and int m is equals to edges dot size. That is the total number of edges are m. Yeah. So I have taken 2 to the power 30 minus 1. That is, uh, if I am taking its bitwise representation, it is something like 1 1 1 1 1 goes until I guess 29 30 times. Just for initialization, I have taken this value as initial value of the AND, so that the AND value can easily be updated for next times. Yeah, this is just initialization of parent vector, size vector, and AND vector for each node. Yeah. So here I am going to edges. Yeah, I am iterating to edges vector. U is E of 0, V is E of 1, W is E of 2. What I have done here is, okay, so first of all, I have to merge elements U and V if and only if they are like if they are already a part of, wait, I have done here is, yeah. So I have updated the AND value of the node U with this edge weight so that I can directly update the edge value, like AND value. Wait, I have did I did this because I have to consider all the edge weight values of the component, whether it like if I am taking its merge value or not. It is not necessary, but I have to update this edge value, like AND value of the node for every case. Okay, so if the leader, if these are not belonging to same component, I have to merge them because there is edge between U and V. What I have done here is just merging these elements U and V. And else, if these are a part of same component, then also I have to update the AND value of the leader of this component. Then what I have to do is, this is just the answer vector which I have to return at the end. So I am iterating to each query where S, the source node is Q of 0, the target node is Q of 1. I am just again just checking if these are not a part of same component, just push back -1 to the answer vector. Else just push back the AND value of that complete component, and just returning this vector. Now let's submit this code. See, it is taking some time. I don't know why, but uh, previously I have submitted this problem. It is getting accepted. So if you are new to this joint set union, then this question will be like somewhat difficult for you. So I would suggest you to read some articles on CP algorithms on this joint set union if you find this problem difficult. Otherwise, thanks for watching.